Hi and welcome. Today I'm going to be talking about representing a function as a power series. Okay. Okay. And there are a couple of methods and two questions associated with this. First, I want to define a power series. A power series is given by this equation. Okay. So that's our power series. And two questions. One, given a function, f of x, what is its power series? Two, once you find the power series, when can we represent the function f of x by the power series? Okay. I'm going to focus in on question one mainly, but I will say that for two, so answers or hints for question two is typically it involves a ratio test, root test, or other tests for convergence or divergence. And we've had numerous tests for divergence or convergence. Okay. Now, the main point of today's lecture is question one. How can I represent a function by its power series? And there's going to be a couple of methods. One is going to be called composition, integration, and differentiation. Okay. There's another method, but it's the point of the next of an entire section in calculus. Okay, it's just one section, and that's Taylor or Maclaurin series. And this is for later. Okay. But let me give you an example of these main methods right here, using composition, integration, or differentiation. Here's going to be my example. Find a power series representation for this function. And the function is f of x equals this arc tangent of x. Okay. Well, I'm going to use a couple of methods here, but one thing that is going to be especially useful is that this arc tangent of x, this is the antiderivative of 1 over 1 plus x squared. then I'm going to use the fact, this is going to be a key fact for all or for most representations. Key is going to be the geometric series. And the geometric series says, hey, this function g of x, which is 1 over 1 minus x, that is this series of 1 plus x squared plus x cubed, and so on, which I can write as the summation from n equals 0 to infinity of x to the n. Okay? And I'm going to go ahead and use this geometric series, and I'm going to do composition here. So first of all, g of minus x, I'm going to call this a new function. I'm going to call this h of x. This is going to be replacing x by negative x. That's what composition is. So now I get 1 over 1 plus x squared. And this will be equal to 1 minus x plus x squared minus x cubed, and so on. And then I get to represent this by the summation from n equals 0 to infinity of minus 1 to the n times by x to the n. Okay, so here I have that power series representation. Notice h of x is 1 over 1 plus x, not x squared, so that's a typo. Okay, but I do want that x squared there. So if I represent h of x squared and do a composite, this says replace x by x squared. Okay, and this is going to be 1 minus x squared plus x to the 4th minus x to the 6th, and so on. This is the same as the summation from n equals 0 to infinity of minus 1 to the n multiplied by x to the 2n. Great. Notice this function is represented by the series on the right. That is exactly what the arctangent is the integral of. Okay? Let's use this fact to find our representation of arctangent. Arctangent of x, which is what we seek to represent, is this integral of 1 over 1 plus x squared, okay, dx, and that is going to be equal to this integral of 1 minus x squared plus x to the 4th minus x to the 6th, and so on. Or I could just integrate each term, the summation from n equals 0 to infinity of minus 1 to the n times by x to the 2n. Either way I integrate this, if I integrate the series, the antiderivative of 1 will be x. Antiderivative minus x squared, I'll get minus x cubed over 3 plus x to the 5th over 4 minus x to the 7th over 7. Apologize there. The denominator of x to the 5th should be 5, of course. Okay. And so on. Or, hey, I can just do this antiderivative of n equals 0. Oh, and I forgot to put down the antiderivative symbol, so I will do that in red here, of this antiderivative. Okay. So let's rewrite that. Summation from n equals 0 to infinity, and then I'll just integrate each term. Okay. Now, once I anti-differentiate each term, I'm integrating with respect to x. Okay, so the minus 1 to the n stays the same, but the power of x goes up by 1. So this is 2n plus 1 over 2n plus 1. And this is exactly what I get if I integrated each term of the series. When n is 0, I get x to the first power. When n is 1, I get negative x cubed over 3. When n is 2, I get x to the fifth over 5, and so on. So one thing you might say to me is, hey, shouldn't each of these have a plus a constant of integration? And I would say technically you're right, but note the constant of integration, it needs to have the same value of the arctangent. So this arctangent of 0 needs to be equal to this right-hand side, which will be a lot of zeros. Those are all 0 plus c. Since those are all zeros inside the parentheses, and arctangent of 0 is 0, c is 0. So yes, technically I should include that constant of integration, but I'm going to erase it because it is 0 after all. Okay, so this is the power series representation of the arctangent. Okay, so I'll label this as the power series representation. After all, I have that it equals arctangent. Now let's move on to question 2. When can we use the power series representation? And the answer is going to come from the ratio test. Okay, and I'm going to let an be equal to x to the 2n plus 1. I'll drop the alternating sign over 2n plus 1. Okay, so I'm going to have to compute this limit as n goes to infinity of a sub n over a sub n plus 1 over a sub n. And that will give us this limit. But for n plus 1, remember, I replace n by n plus 1. So this will be x to the 2n plus 1 plus 1 divided by 2n plus 1 plus 1. And now I'm going to invert and multiply. Okay, well, if I invert and multiply, I'll have x to the 2n plus 3 over 2n plus 3 multiplied by 2n plus 1 divided by x to the 2n plus 1. Okay, I get to cancel all of that with all of that, and I'm left with a 2 there. Okay, so I have x squared in the numerator. So I'm going to have x squared here, and it's going to be multiplied by 2n plus 1 over 2n plus 3, and I can evaluate this limit. It's 1, so I'm left with this x squared, and that is the limit. The ratio test tells us this. the ratio test says when L is less than 1, i.e. x in absolute value is less than 1, the series converges. When L is bigger than 1, i.e. absolute value of x is bigger than 1, the series diverges. And we must use another test when x is equal to plus or minus 1. Okay, so if x equals 1, well, we get this series. Our original series was minus 1 to the n times by x to the 2n plus 1. Okay, and our x goes away because 1 to any power is 1. So minus 1 to the n divided by 2n plus 1, starting with n equals 0 and going to infinity. We're going to use the alternating series test with b sub n equal to 1 over 2n plus 1. The first thing that we're going to check is, hey, b sub n, this is 1 over 2n plus 1, and that's bigger than or equal to b sub n plus 1, which is going to be 1 over 2 n plus 1 plus 1, which is 1 over 2n plus 3. So it's decreasing. The second thing is that this limit, as n goes to infinity of b sub n, is going to be equal to this limit as n goes to infinity of 1 over 2n plus 1. And that is 0. So it's convergent for x equals 1. Okay. Now, if x equals negative 1, we get this summation from n equals 0 to infinity. And I'm going to have minus 1 to the n. Remember, I'm going to plug in x is 2n plus 1. Okay. Divided by 2n plus 1. And let's just double check, I got the series right. So I'm just plugging in x equals minus 1 here, and that looks right. Okay. Well, this series I can simplify to be n equals 0 to infinity of minus 1, since they both have the base of minus 1 there. This is going to be x to the 3n plus 1 divided by 2n plus 1. Okay. And, notice when n equals 0, I get minus 1. When n equals 1, I get minus 1 to the power of 4 divided by 3. When n equals 2, I get minus 1 to the 7th power. Okay, so why don't I write a few of these terms down? N equals 0 gives me minus 1. The next term is going to be n equals 1. That's going to be a positive 1 in the numerator. This is going to be 1 over, the denominator will be 3. When n equals 2, the denominator is going to be 5. And the minus 1 power when n is 2 is going to be 7, so that's negative. Okay. And the next term will be n equals 4. Excuse me, will be 3, n equals 3. So that will be 7. And minus 1 will be to the power of 10. So that'll be positive, and then it'll be negative, and it keeps going. This is again an alternating series, and this happens to be almost identical to the x equals 1 case. This is convergent by the alternating series test. With, again, the same b sub n. B sub n is just going to be the non-negative part, and that's 1 over 2n plus 1. By the work that we did above, it's convergent. Okay, so our final conclusion is that this arc tangent of x, we can write equalities. It's equal to minus 1 to the n equals 0 to infinity, of x to the 2n plus 1 divided by 2n plus 1. And I can use this power series representation whenever x is between minus 1 and 1. Okay. So now I found a representation for a function as a sum, an infinite sum of powers of x's. One application that's going to be really nice, it's hard to integrate the arctangent of x, but I can integrate powers of x pretty easily. I can do a lot of things with powers of x's. Okay, so that's a wrap for today. We'll talk more and give further examples about representing power series as functions. After all, these are the two main questions. I give you a function, you tell me its power series. Once you give me that power series, I'm going to ask you when I can use it. And here are some hints as to when or how I would answer those questions. If I'm giving a function, one of the key things I'm going to use, and I'm going to write this here, let's write it in red, is it's also useful to write down the geometric series. That's another helpful one. But we can use composition, integration, differentiation, geometric series, and once you learn it, Taylor-Maclaurin series. To help us answer when we can represent the function, we will want to use our tests for convergence or divergence.